Okay, this is going to be the lecture over section 3.4, uniform circular motion. So when a particle moves in a circular path with radius r and a constant speed v, it has an acceleration with magnitude, radial acceleration is equal to v squared divided by r. And that is always directed towards the center of the circle and perpendicular to the instantaneous velocity at each instant. So you can see the picture here where we've got the acceleration is always pointed in this way. And then the velocity, the instantaneous velocity vector, is always at a tangent to the path of motion. Okay, so we've got a car speeding up along a circular path. So we've got our car here, we've got the path here. So we can see the component of acceleration parallel to the velocity as the car changes speed, and then we've got a component of acceleration that's perpendicular. The acceleration is pointed this way, the velocity is pointed this way, so we see the component lining up along that, and then we see the component that is radial. So again, the velocity vector is always going to be tangential to the path of motion. So in uniform circular motion, an object moves at constant speed in a circular path and its acceleration is perpendicular to its velocity. So the component of acceleration perpendicular to the velocity changes the car's direction, and the component of acceleration parallel to velocity changes the car's speed. So if we have in uniform circular motion, we've got an object moves at a constant speed and its acceleration is perpendicular to its velocity. So it's always going to be pointing this way. So a constant speed along a circular path, you're going to have the acceleration going to be exactly perpendicular to the velocity. So here we had acceleration where it was accelerating along this. So we've got a component this way and this way. We've got a car here that's slowing down, so we have acceleration pointed this direction, again with components perpendicular as well as in opposition to the velocity vector. Here, it's moving at a constant velocity, so there's nothing that's changing this particular velocity, so that all of the acceleration is pointed towards the center of the circle. So if we go through and if we attempt to derive what's going on, we're going to take a look at figure 3.21 here. And it's going to show an object represented by a dot that's moving with constant speed in a circular path with radius r at center O. The object moves from A to B and during a particular distance in a particular time. So the vector change in the velocity during this time is shown. So you can see the change in these particular vectors here. It's represented by this. There's a change in the angle between them. So the corresponding change in velocity is reflected here. You can see the acceleration in uniform circular motion always points towards the center of the circle. So if you take this vector right here and divide it by, let's see, the two triangles formed in 3.21a and the other in 3.21b. If you put the corresponding parts together, put this and this as divided by this or this, seeing as how they're similar triangles, you can get this particular relationship. If you turn it around, you can see the change in the velocity vector is equal to v1r times the change in s. We know the magnitude of the average acceleration during this time is considered to be the change in v over the change in t, which we discussed in the previous section. We substitute that in. And we can also take this expression right here. If we divide it by delta t, this is what we come up with. So the magnitude A of the instantaneous acceleration at point A is the limit of that expression. And as point B gets closer and closer to point A, this is the result that we end up with. The limit as delta t approaches 0. We have the velocity here, which doesn't change. We have the r here. We do have this change and this change. This is just defined as speed. If we define this just as the speed, we can change that to the velocity value. And then we get that the radial acceleration is v squared over r. The magnitude is going to be in meters per second squared. So not only does the direction of the velocity constantly change as the object moves around, but the direction of the vector also changes. That's why it spins around in a circle like it does. The radial acceleration also increases as the square of the speed, which is what we've just derived. So because the acceleration of an object in uniform circular motion is always directed towards the center of the circle, it's sometimes called centripetal acceleration. Centripetal, of course, means seeking the center. You can see the directions of the acceleration vector and the velocity vectors. If you look at projectile motion, you can kind of see sort of the same thing going on. The acceleration is always down, always pointed towards the Earth, but the velocity vector also changes. So it's not really that odd to see how these vectors interplay with each other. You can see here that this acceleration downward is always constantly trying to force this velocity vector down. Same thing with this, as it's always pointing towards the center, it's always causing this velocity vector to bend around the circle. Again, we have problems here that would be good for you to work. I will encourage you to do so.